Music transformer, generating music with long-term structure. Music relies heavily on repetition to build structure and meaning. Self-reference occurs on multiple time scales, from motifs to phrases to reusing of entire sections of music, such as in pieces with ABBA structure. The Transformer, Vaswani et al., 2017, a sequence model based on self-attention, has achieved compelling results in many generation tasks that require maintaining long-range coherence. This suggests that self-attention might also be well-suited to modeling music. In musical composition and performance, however, relative timing is critically important. Existing approaches for representing relative positional information in the transformer modulate attention based on pairwise distance. Shaw et al., 2018. This is impractical for long sequences such as musical composition, since their memory complexity for intermediate relative information is quadratic in the sequence length. We propose an algorithm that reduces their intermediate memory requirement to linear in the sequence length. This enables us to demonstrate that a transformer with a modified relative attention mechanism can generate minute-long compositions, thousands of steps, 4 times the length modeled in Orr et al., 2018, with compelling structure, generate continuations that coherently elaborate on a given motif, and in a SEQ2-SEQ setup generate accompaniments conditioned on melodies. 1. We evaluate the transformer with a relative attention mechanism on 2 datasets, JSB chorales and piano EQ competition, and obtain state-of-the-art results on the latter. Introduction. A musical piece often consists of recurring elements at various levels, from motifs to phrases to sections, such as verse-chorus. To generate a coherent piece, a model needs to reference elements that came before, sometimes in the distant past, repeating, varying, and further developing them to create contrast and surprise. Intuitively, self-attention, Parikh et al., 2016, appears to be a good match for this task. Self-attention over its own previous outputs allows an autoregressive model to access any part of the previously generated output at every step of generation. By contrast, recurrent neural networks have to learn to proactively store elements to be referenced in a fixed size state or memory, potentially making training much more difficult. We believe that repeating self-attention in multiple, successive layers of a transformer decoder, Vaswani et al., 2017, helps capture the multiple levels at which self-referential phenomena exist in music. In its original formulation, the transformer relies on absolute position representations, using either positional sinusoids or learned position embeddings that are added to the per-position input representations. Recurrent and convolutional neural networks instead model position in relative terms, RNNs, through their recurrence over the positions in their input, and CNNs by applying kernels that effectively choose which parameters to apply based on the relative position of the covered input representations. Music has multiple dimensions along which relative differences arguably matter more than their absolute values. The two most prominent are timing and pitch. To capture such pairwise relations between representations, Shaw et al., 2018, introduce a relation-aware version of self-attention which they use successfully to modulate self-attention by the distance between two positions. We extend this approach to capture relative timing and optionally also pitch, which yields improvement in both sample quality and perplexity for JSB chorales. As opposed to the original transformer, samples from a transformer with a relative attention mechanism maintain the regular timing grid present in this dataset. The model furthermore captures global timing, giving rise to regular phrases. The original formulation of relative attention, Shaw et al., 2018, requires OL2D memory, where L is the sequence length and D is the dimension of the model's hidden state. This is prohibitive for long sequences such as those found in the Piano EEC competition dataset of human-performed virtuosic classical piano music. In section 3.4, we show how to reduce the memory requirements to OLD, making it practical to apply relative attention to long sequences. The Piano EEC competition dataset consists of MIDI recorded from performances of competition participants bearing expressive dynamics and timing on the granularity of less than 10 milliseconds. Discretizing time on a fixed grid that would yield unnecessarily long sequences, as not all events change on the same timescale. We hence adopt a sparse MIDI-like event-based representation from Orr et al., 2018, allowing a minute of music with 10 millisecond resolution to be represented at lengths around 2K, as opposed to 6K to 18K on a fixed grid representation with multiple performance attributes. As position in sequence no longer corresponds to time, a priori it is not obvious that relative attention should work as well with such a representation. However, we will show in section 4.2 that it does improve perplexity and sample quality over strong bass lines. We speculate that idiomatic piano gestures such as scales, arpeggios and other motifs all exhibit a certain grammar and recur periodically. Hence, knowing their relative positional distances makes it easier to model this regularity. This inductive bias towards learning relational information, as opposed to patterns based on absolute position, suggests that the transformers with relative attention could generalize beyond the lengths it was trained on, which our experiments in section 4.2.1 confirm. Contributions. Domain contributions. We show the first successful use of transformers in generating music that exhibits long-term structure. Before our work, LSDMs were used at time scales of 15s, approximately 500 tokens, on the Piano EEC competition dataset, Orr et al., 2018. Our work show that transformers not only achieve state-of-the-art perplexity on modeling these complex expressive piano performances, but can also generate them at the scale of 60s to 2000 tokens with remarkable internal consistency. Our relative attention mechanism is essential to the model's quality. In listening tests, see section 4.2.3, samples from models with relative self-attention were perceived as more coherent than the baseline transformer model from Vaswani et al., 2017. Relative attention not only enables transformers to generate continuations that elaborate on a given motif, but also to generalize and generate inconsistent fashion beyond the length it was trained on. See section 4.2.1. In a SEQ2-SEQ setup, transformers can generate accompaniments conditioned on melodies, enabling users to interact with the model. Algorithmic contributions. The space complexity of the relative self-attention mechanism in its original formulation, Shaw et al., 2018, made it infeasible to train on sequences of sufficient length to capture long-range structure in longer musical compositions. Addressing this, we present a crucial algorithmic improvement to the relative self-attention mechanism, dramatically reducing its memory requirements from OL2D to OLD. For example, we reduce the memory consumption per layer from 8.5 GB to 4.2 MB per head, from 1.1 GB to 0.52 MB for a sequence of length L equals 2048 and hidden state size D equals 512 per head, DH equals 64. where number of heads is h equals 8. See Table 1, allowing us to use GPUs to train the relative self-attention transformer on long sequences. Sequence models have been the canonical choice for modeling music, from hidden Markov models to RNNs and long short-term memory networks, e.g. Eckenschmidt-Huber 2002, Liang 2016, or et al. 2018, to bidirectional LSTMs, e.g. Hadjaras et al. 2017. Successful application of sequential models to polyphonic music often requires serializing the musical score or performance into a single sequence, for example by interleaving different instruments or voices. Alternatively, a 2D piano roll-like representation, see point 1 for more details, can be decomposed into a sequence of multi-hot pitch vectors, and their joint probability distributions can be captured using restricted Boltzmann machines, Smolensky, 1986, Hinton et al., 2006, or neural autoregressive distribution estimators, NADE, Larischel and Murray, 2011. Piano rolls are also image-like and can be modeled by CNNs trained either as generative adversarial networks, e.g. Dong et al. 2018, or as orderless NADEs, Urey et al. 2014, 2016, e.g. Huang et al. 2017. Latner et al. 2018 use self-similarity in style transfer fashion, where the self-similarity structure of a piece serves as a template objective for gradient descent to impose similar repetition structure on an input score. Self-attention can be seen as a generalization of self-similarity. The former maps the input through different projections to queries and keys, and the latter uses the same projection for both. Product self-attention is the mechanism at the core of the transformer, and several recent works have focused on applying and improving it for image generation, speech, and summarization. Parmar et al. 2018, Povey et al. 2018, Liu et al. 2018. A key challenge encountered by each of these efforts is scaling attention computationally to long sequences. This is because the time and space complexity of self-attention grows quadratically in the sequence length. For relative self-attention, Shaw et al. 2018, this is particularly problematic as the space complexity also grows linearly in the dimension, or depth, of the per-position representations. Model 3.1 Data representation. We take a language modeling approach to training generative models for symbolic music. Hence we represent music as a sequence of discrete tokens, with the vocabulary determined by the dataset. Datasets in different genres call for different ways of serializing polyphonic music into a single stream and also discretizing time. The JSB chorale dataset consists of 4 parts: scored choral music, which can be represented as a matrix where rows correspond to voices and columns to time discretized to 16th notes. The matrix's entries are integers that denote which pitch is being played. This matrix can then be serialized in raster scan fashion by first going down the rows and then moving right through the columns. See point 1 for more details. Compared to JSB chorale, the piano performance data in the Piano EEC competition dataset includes expressive timing information at much finer granularity and more voices. For the Piano EEC competition, we therefore use the performance encoding proposed by Orr et al. 2018, which consists of a vocabulary of 128 note underscore on events, 128 note underscore offs, 100 time underscore shifts, allowing for expressive timing at 10 milliseconds, and 32 velocity bins for expressive dynamics. See point 2 for more details. 3.2 Background. Self-attention in Transformer. The Transformer decoder is an auto-regressive generative model that uses primarily self-attention mechanisms and learned or sinusoidal position information. Each layer consists of a self-attention sublayer followed by a feed-forward sublayer. The attention layer first transforms a sequence of LD-dimensional vectors x equals x1, x2, xl into queries q equals xwq, keys k equals xwk, and values v equals xwv, where wq, wk, and wv are each d times d square matrices. Each L times D query, key, and value matrix is then split into HL times DH parts or attention heads indexed by H and with dimension DH equals DH, which allow the model to focus on different parts of the history. The scale.product attention computes a sequence of vector outputs for each head as ZH equals attention QH VH equals softmax QH greater than square root TH VH. 1. The attention outputs for each head are concatenated and linearly transformed to get Z AL by D-dimensional matrix. A upper triangular mask ensures that queries cannot attend to keys later in the sequence. For other details of the transformer model, such as residual connections and learning rates, the reader can refer Vaswani et al., 2017. The feed-forward FF sublayer then takes the output Z. From the previous attention sublayer, and performs two layers of pointwise dense layers on the depth D dimension, as shown in equation 2. W1, W2, B1, B2 are weights and biases of those two layers. FFZ equals ReLU ZW1 plus B1, W2 plus B2. (3.3) Relative positional self-attention. As the transformer model relies solely on positional sinusoids to represent timing information, Shaw et al. 2018 introduced relative position representations to allow attention to be informed by how far two positions are apart in a sequence. This involves learning a separate relative position embedding of shape H, L, DH, which has an embedding for each possible pairwise distance r equals jk minus iq between a query and key in position iq and jk respectively. The embeddings are ordered from distance minus l plus 1 to 0, and are learned separately for each head. In Shaw et al. 2018, the relative embeddings interact with queries and give rise to ASRel. An L times L dimensional logits matrix which modulates the attention probabilities for each head as relative attention equals softmax QK greater than plus SRel square root DH V3. We dropped head indices for clarity. Our work uses the same approach to infuse relative distance information in the attention computation while significantly improving upon the memory footprint for computing SRel for each head. Shaw et al. 2018 instantiate an intermediate tensor R of shape L, LDH containing the embeddings that correspond to the relative distances between all keys and queries. Q is then reshaped to an L1 DH tensor and SRel equals QR greater than 2. This incurs a total space complexity of OL2D, restricting its application to long sequences. 3.4 Memory-efficient implementation of relative position-based attention. We improve the implementation of relative attention by reducing its intermediate memory requirement from OL2D to OLD. With example lengths shown in Table 1, we observe that all of the terms we need from Q are greater than are already available if we directly multiply Q with the relative position embedding. After we compute QER greater than its IQ, our entry contains the dot product of the query and position IQ with the embedding of relative distance R. However, each relative logit IQ JK in the matrix SREL from equation 3 should be the dot product of the query in position IQ and the embedding of the relative distance JK minus IQ to match up with the indexing in QK greater than. We therefore need to skew QER greater than so as to move the relative logits to their correct positions as illustrated in figure 1 and detailed in the next section. The time complexity for both methods are OL2D, while in practice our method is 6x faster at length 650. Figure 1. Relative global attention. The bottom row describes our memory-efficient skewing algorithm, which does not require instantiating our top row, which is OL2D. Gray indicates masked or padded positions. Each color corresponds to a different relative distance. Table 1. Comparing the overall relative memory complexity, intermediate relative embeddings RR plus relative logits SREL. The maximal training lengths that can fit in a GPU with 16 GB memory assuming DH equals 64, and the memory usage per layer per head in MB. (3.4.1) The skewing procedure. Hence, we proposed skewing procedure to transform an absolute by relative IQ index matrix into an absolute by absolute IQ JK index matrix. The row indices IQ stay the same while the column indices are shifted according to the following equation: JK equals R minus L minus 1 plus IQ. For example, in figure 1, the upper right green dot in position 0, 2 of QER greater than after skewing has a column index of 2 minus 3 minus 1 plus 0 equals 0, resulting in a position of 0, 0 in SREL. We outline the steps illustrated in figure 1 below. 1. Pad a dummy column vector of length L before the leftmost column. 2. Reshape the matrix to have shape L plus 1 L. This step assumes NumPy-style row major ordering. 3. Slice that matrix to retain only the last L rows and all the columns, resulting in the L matrix again, but now absolute by absolute index, which is the SREL that we need. (3.5) Relative local attention for very long sequences. The quadratic memory requirement of even baseline transformer is impractical. Local attention has been used, for example, in Wikipedia and image generation. Liu et al. 2018, Parmar et al. 2018, by chunking the input sequence into non-overlapping blocks. Each block then attends to itself and the one before, as shown by the smaller thumbnail on the top right corner of figure 2. To extend relative attention to the local case, we first note that the right block has the same configuration as in the global case, see figure 1, but much smaller, LM2, where M is the number of blocks, and MB the resulting block length as opposed to L2. The left block is unmasked with relative indices running from -1 top right to 2n plus 1 bottom left. Hence, the learner for the local case has shape 2n-1 n. Similar to the global case, we first compute QER greater than and then use the following procedure to skew it to have the same indexing as QK greater than, as illustrated in figure 2. 1. Pad a dummy column vector of length n after the rightmost column. 2. Flatten the matrix and then pad with a dummy row of length n-1. 3. Reshape the matrix to have shape n plus 1, 2n-1. 4. Slice that matrix to retain only the first n rows and last n columns, resulting in the n matrix. In this work we demonstrated that the transformer equipped with relative attention is very well suited for generative modeling of symbolic music. The compelling long-term structure in the samples from our model leaves us enthusiastic about this direction of research. Moreover, the ability to expand upon a primer, in particular, suggests potential applications as creative tool. The significant improvement from relative attention highlights a shortcoming of the original transformer that might also limit its performance in other domains. Improving the transformer's ability to capture periodicity at various time scales, for instance, or relations between scalar features akin to pitch could improve time series models. Our memory-efficient implementation enables the application of relative attention to much longer sequences such as long texts or even audio waveforms, which significantly broadens the range of problems to which it could be applied.